I think we're going to really, we're going to kind of touch on a lot of things that were said earlier this morning about bringing our bridge experience forward, condition state and element level history, and a couple other items that we've talked about this morning, but we'll go ahead and get rolling. So Eisenhower Johnson Memorial Tunnel inspections, not really going to focus on defects as much as just lessons learned on the implementation of the NTIS and developing a program for CDOT. Quick agenda. In fact, we'll just cruise through this. The CDOT and NTIS rollout, so kudos to CDOT who, knowing that NTIS was coming, really tried to get out ahead of the NTIS and really wanted us to get out and get inspections performed prior to NTIS coming out. So contract was let in 2014. We got started, took draft manuals out of the SNIDI and the TOMI, and really started to develop what CDOT's program would look like, and actually got a couple inspections completed prior to the NTIS rollout, which in August of 2015 pretty much told us they weren't meaningful anymore, which proved to be a blessing in disguise. So that silver lining of NTIS kind of putting the kibosh on where we were made us take a step back and really have a chance to develop CDOT's program in its entirety. So in a partnership between Stantec, Gannett Fleming, and actually Brierley Associates, we were able to go around and do an NFPA gap analysis. And quickly what that is just to go around and look at all of CDOT's tunnels with the mechanical and electrical and NFPA experts from Gannett Fleming, and really kind of dial in where CDOT's tunnels were or weren't in accordance with the NFPA metrics. So by doing that, we were able to interview all of the operators, all the superintendents, and a lot of the engineers throughout CDOT while we were developing their manual. And in developing the manual, it was looking at the SNIDI elements, taking the definitions, adding sub-elements, creating agency-defined elements, and really putting in that definition to a manual that kind of let everybody read between the lines. The other blessing in disguise with NTIS is we had the ability to take all the historical structural inspections on tunnels and reset the schedule, so we could apply that to fit into CDOT's overall program. And obviously it gave us a lot of time talking to everyone at CDOT to gather all the historical information, a lot of which is institutional. So a lot of interviews and documentation of that institutional knowledge. As you can see, we don't have a lot of cut and cover tunnels, Colorado. It's a lot of rock. We've got 35 total tunnels, 24 on system or state owned, 5 we've deemed complex. 2 of those are actually closed, so there's really 22 on system that we're responsible for, 11 local agency or off system tunnels. Like I said, we have extensive rock. You can see by the map that yes, we have 1 tunnel in downtown Denver, and that is the one cut and cover that we have. It's the only one that will have a load rating. And everything else is slab on grade. And one of the other unique things here is that, like Eisenhower Johnson, you can see on the right, all of our plenums, if they exist, are above the roadway. So both plenums are above, somewhat unique. So in the element development, our real goal was to reduce subjectivity and increase the repeatability in this program moving forward. So part of what we're able to do with developing CDOT's program was develop a manual and also develop their asset management logic. So deterioration modeling, projections, and a lot of that comes back into developing the data that we're going to gather and make sure that that data is meaningful. So we were able to create a lot of subcomponents as well as the agency-defined elements. And a lot of those interviews led to those hot button issues. And I think that's the biggest lesson learned from the program implementation is really knowing the inventory and knowing what drives the maintenance of those tunnels. So Eisenhower Johnson, we'll get into a couple stats on that. Opened in 1973 for Eisenhower, 1979 for Johnson. And no, it's not the President Johnson. Carries I-70 about 60 miles west of Denver. For those of you who don't know, it's about 9,000 feet in length, approximately 11,000 feet in elevation, sloping west to east. So a lot of times you'll hear it called Straight Creek tunnels as well, and that's the creek on the west end. Everything was drill and blast, and one of the biggest problems we had, which is why you see the drift construction method there, is it actually passes through a fault line. So needless to say, there's some interesting structure-earth interaction. ADT is about 35,000 between both bores, so not a ton, about 50,000 in July and August. fully transverse. We had 31 SNIDI elements and 10 agency-defined elements in this one, including a wastewater treatment plant. So for those of you who don't know, your Coors beer starts with a wastewater treatment plant. Drift construction on the left, and just kind of a cool historical photo of them setting the ceiling panels and the divider wall in the plenum. One of the interesting things here is that earth pressure, because it is rock, not cut and cover, it actually fractured a lot of the steel sets, and after board, it caused the floor to rise almost 1.5 feet. As we kind of get towards focusing on a lot of the mechanical and electrical side, the fan layout, just to give you an idea, the right is Eisenhower, obviously duplicated at both ends. So we have 8 fans in each ventilation building for Eisenhower and 6 in each end for Johnson, for the Johnson bore. 1.6 million cubic feet per minute, so not small change. The electrical layout, one thing we found really useful in terms of just kind of getting everybody on the same page as we merge industries is a flow chart like this highlights what gear and where it falls so that everybody knows what we're quantifying and what we're actually documenting in a report. Little overview of NTIS. Quick inspection details. We did this in 4 weeks. So we had 8 staff in the roadway. And no, this photo is not staged, I promise. But 8 staff in the roadway, 6 staff in the plenum, 1 week for mechanical and electrical staff to run through both ventilation buildings as well as all the cross passes. NETA testing we actually completed separately. And in fact, they're still completing that right now. So I think the biggest lesson learned, and then I want to get this passed over, is as we bring in people, a lot of us have, as we just found out, a lot of us have the bridge inspection, that element level background. That is, it turns out, is a pretty unique mindset. Bringing in, especially the geologists, they have their own terminology, and getting everybody to write in similar fashion and take notes in a similar fashion. We did a lot of pre-inspection training. We wrote the manual ahead of time with a lot of guidance in between all the defects, and we had those test tunnels that, well, what turned out to be test tunnels. And even then, getting about 14,000 lines of data out of our inspection, QCing that data with everybody's terminology was difficult. So I stress that ahead, is getting everybody on the same page and knowing your inventory. Stationing. We were able to develop essentially a stationing system that would work in all of Colorado's tunnels. That way we can use that across the inventory. Note-taking to environment. We actually had a laptop get doused by a deluge test, so always have paper with you. And really the scope of work is define that with your agency. Know what they want, know what they need. Is it 10% of a liner to be sounded? Really get into those details. And I think for the electrical and mechanical is to be accompanied by operators and those maintainers. They have an institutional knowledge and working on that equipment every day. And obviously every long tunnel needs commuting capability. So we highly recommend bicycles. And I will pass it over to Brian.
Good afternoon, everybody. Nick touched on it. Agency-defined elements was pretty key for us with CDOT, the NTIS, and the SNTI. Kind of boil mechanical and electrical down into a handful of things, and I'll talk a little bit about it. But we spent a good bit of time in developing the Colorado Tunnel Inspection Manual, we call it the CTIM, in defining sub-elements under electrical distribution system, for example, which is 10500 in the SNTI, and broke it down into the sub-elements they list, so we can then score them individually and roll scores up. Again, more information for the owners to use as far as tracking maintenance and the asset management that Nick talked about earlier. The institutional knowledge is critical. You're coming into a tunnel, meeting people that have worked there for years and years. They know the reliability of their systems, so in advance of even test operating fans or generators or switchgear elements, you ask them those questions about reliability up front to make sure that you're not going to cause a problem in testing a piece of equipment or test it this time of day versus that time of day based off of traffic. Paul may touch on it. Scheduling fan testing is pretty critical. They don't typically do it with heavy traffic, so we accommodate those types of things. Getting drawings, equipment cut sheets. ahead of time is important so you don't get lost when you're moving around. The Eisenhower Johnson tunnel has space over each tube, but then has multi-level in the portal building between the tubes. You have to get up and over and around, and walking and climbing steps at 11,000 feet. You can lose your breath real quick, and you only want to do that when you need to do that. For larger facilities, which we did for Eisenhower Johnson, and we just are getting ready to do the Hanging Lakes pre-inspection visit, go out, get the lay of the land, ask some of these questions up front, get these documents up front, so when you're out there, you're ready to hit the ground running for the inspection. Safety is important. Again, in discussions with the owner, identify what they consider confined spaces. Some places may be confined spaces and they don't consider them as such. So use your engineering judgment when entering into those types of spaces. And make sure you have the right PPEs. On the mechanical side, fans rotate to blow air into the vent shafts. Particularly for the mechanical or electrical inspectors that are in the vicinity of those fans when they're moving hundreds of thousands of CFM, be cognizant that loose clothing articles, name tags, badges, lanyards, and things you need to secure safely. Noise is another key element. Ear protection is required. Arc flash, again, at CDOT, we did have the NETA testing performed. Again, electrical equipment that is operating, if the doors are open, can cause arc flash potentially. Just be cognizant of that if you're in the neighborhood of that equipment when that happens. Otherwise, stand back and let the professional testers do that. One of the things that SNTA talks about in the red box, tunnels with twin bores may have separate systems and be considered as two. The challenge is, and this was true for Eisenhower Johnson, electrical systems can be integrated between the two tubes and between the two portal ends. So what we did with CDOT, and we've continued to use this other places, is we take the electrical system that's on the east portal building and we associate it with the eastbound traffic lane. Again, the inventory that was submitted to FHWA said there was 2 bores with 2 electrical systems, so one has to go with one and one goes with the other. Same thing could be true for fire detection. Frequently, there's a loop system that will run through the tunnel. So again, we associate one end with one and one with the other. And then what's in the traffic goes with the traffic direction, obviously. Listing, there's the 6 SNTI elements that electrical takes responsibility for. And again, for CDOT, we broke those down into some of those agency-defined elements that were part of that quantity that Nick mentioned earlier. Some of the subcomponents under electrical distribution or emergency distribution system, and these are all listed in the SNTI. Question is, are they all really as important subcomponents to each other? Certainly the last thing in the list, your electrical outlets and receptacles, are not as critical as elements like panel boards, transformers, or transfer switches, but they are listed under 10500 as sort of a equal sub-element. As anybody that went through that training, the trainers told you, give your score and be able to argue your position or describe your position if you're challenged on the score. So we take that to heart, and again, key elements that are closer to the top of that list take a stronger weight, as it were, when scoring those elements. Electrical systems are different than ventilation fans. So a fan has bearings, belts, chains. If a bearing is bad or a fan belt is broken, then the entire unit of the fan is essentially not operational. One failed panel board or one measly failed receptacle, it does not mean that the entire electrical distribution system fails and would score, critical finding or a condition state 4. So again, use your judgment when scoring those types of elements. Fire life safety security systems. I've got a photo of a fire pump there. CDOT actually has a standpipe system and a fire suppression system. Because of their cold climate temperatures, they actually have boilers that heat the water and keep that system operational. So there's some sub-elements that fall under fire protection that you would not normally have in a warmer climate that we had to consider when scoring fire protection. And Paul's going to take over.
So I'm just going to talk through the procedures I go through for mechanical inspection. Brian touched on a pre-inspection site visit. My biggest fear when I'm doing a mechanical inspection is I'm going to go out there and not have enough time to test all the devices I have to. And as you know, it'd be very expensive to go back out to Colorado or extend your visit. So we put a lot of effort in being ready for the inspection. I've even gotten to the point where I've developed a pre-inspection manual where I make sure I have every point in there that I want to touch on with the operators. Their logistics, their fan operations, test procedures. I have copies of my basic forms in there, and I'll customize them to what I'm going to see when I get back out there. So then my next step is I customize the forms for what I'm going to see out there. I like to have a form for every piece of equipment that I'm going to run into, have it pre-numbered. I just want to be able to fly through the inspection, not a fly-through inspection, but I don't want to get bogged down in not having the right paperwork. So at the Johnson Tunnel, which you heard was built later after the Eisenhower Tunnel, had a very complicated drive system on the fans. They have 2 motors, 2 clutches, 8 bearings, in addition to the 2 fan bearings. So we made up a sketch based on our site visit and looking at drawings and gave each bearing a number and then loaded those bearings into our inspection forms. And as it turned out, some of those bearings had temperature issues, so the way we addressed it in the forms worked out really well. We even had the form in Excel, and the Excel form did our calculations for us on the temperature differential, which I'll explain more about in a minute. So once we got on site, our goal was to collect all the data, or as much data as we could electronically, so we didn't have to go back to the office and start transcribing our hand notes into our forms. So you can see a picture of me there working on a laptop. At Eisenhower Johnson, it worked out really well. The month before we got there, Eisenhower Johnson did a test of their brand new fire suppression system, and they turned all their exhaust and supply fans on so they can just make sure the interaction between the two was okay. But in turning all their 600 horsepower fans on high speed, they incurred about a $30,000 electrical demand charge from the utility company. So by the time I got there, they said 1 fan at a time. So it worked out really well. I had time to type all my notes in as we moved along. In the last 3 weeks, we've done inspection at the Queens Midtown Tunnel in New York City. We got there the day after a snowstorm, so the fan floors were full of snow and ice. It's about 30 degrees, and all the fans were creating a pretty strong breeze through there. So picture that same picture. I tried doing that, but I could not take my gloves off long enough to type much. So we went to Plan B. So Plan B is we always have paper copies of our electronic forms. And you're going to go into some spaces where you don't want to take your laptop, like where the sump pumps and stuff are. So my only lesson learned on that is the spiral-bound manuals work much better in the field than the 3-ring binders, just because of the way you can fold them over. So it's a stupid little hint, but it's worth the extra effort to get them bound right. So instruments, the main instrument we use is an infrared thermometer. We have to measure the temperatures of the bearings, the ambient temperature. And what the SNIDI wants to know is what the temperature differential is between the device and ambient. And based on that, you may have to adjust your score on the fans. The picture on the left is a thermal imaging picture that we took. We did have thermal imaging cameras there, but in the end, a handheld is what we were looking for. But the question is, how accurate does that IR thermometer need to be? So I did a test for you. Our company owns 4 devices. I put them in order of cheapest to most expensive. On the left is probably a $50 IR thermometer. The next one is the one I use. It's about $125. The next 2 devices, the one on the right is a thermal imaging camera that cost about $15,000 the day we bought it many years ago. So I took a warm surface and a cooler surface, and I put blue painter's tape on it so that I would have the same emistivity with everything. And I took temperature readings. As you can see, the actual temperature readings are kind of all over the place. So which one's the most accurate, I don't know. But I know that the delta T, that's the number I need. if you look at those numbers, they're pretty close. The two devices on the left are within 0.2 of a degree of each other. So the point I want to make is use the same instrument for all your measurements. If you have two guys running around with two different IR thermometers, you could have bad readings. The other thing you need to know is your distance to spot ratio. The cheap instrument shows you a red dot. I could be 50 feet away and you'll see a red dot. But that cheap instrument has a 10-to-1 ratio. That means 10 inches away from the surface, the diameter of your spot is really 1 inch. So if you're 10 feet away, you could have a 10-inch diameter, and it's measuring everything inside that diameter. So if you don't get close enough, you could be picking up other readings. I got lucky with the device I bought. I didn't realize it, but it actually shows you the size of the dot, and that's what you see on that bearing is the actual size that it's measuring. So, and that comes into play when you're taking bearing measurements and the fan's on high speed, and you have to get close enough to get a reading. You better hang on because you're going to be wobbling. So field work, when I inspect fans, we typically do two inspections. We do a visual inspection and we do an operational test. So when we're doing the visual inspection, we like the fans to be off because you have rotating equipment and you can see it better if it's not spinning around. When we run the fans, we'd like to have them been on for a couple hours so that the bearing temperature stabilize. So one lesson I learned is that you want to go, when you have 28 fans or 44 fans, you want to have a good scorecard where you're keeping track of what you've done, because all those fan numbers are going to start running together. And at Eisenhower Johnson, we were walking around, and between us and the tunnel operators, we were arguing over which ones we had tested already and which ones failed. So on the fly, I did, as you can see there, a little scorecard, but now I go into the field with a much better one. Scoring, I say draw a line and stick to it. You'll learn in the courses that the 1s and the 4s are obvious. You usually argue with yourself about the 2s and the 3s, but read the verbiage in the SNITI. And the one line that I draw is if I hear a belt squeaking and clicking or a little bit of belt flapping, that's a 2, because it's a simple adjustment. A complex adjustment is a 3, and to me that's typically excessive vibration. That means there's a lot more work that has to be done. The other thing we do is we always give notes on why we're scoring, why we came to the score. So what you're seeing here is we're telling them, on some of these, we're telling them the bearing temperatures require a CS3 or a CS4. And what I also did is told them what would have happened if the bearing temperatures weren't high. Would it still be a 3? Would it still be a 4? Just so that the owner knows what's going on.